introduce you today in this X-course lecture to one of the people I follow. It was since Twitter and then on LinkedIn, which is not only a colleague in the area of AI, but also in the area of computer science. And in these times where we have a lot of only focusing in one of the subfields of AI, which is the one related to machine learning, and in machine learning only focusing in one of the subfields of machine learning, which is deep learning, and in deep learning focusing only in one of the subfields, which is generative AI, and in generative AI only focusing in software and products that have to do with chatbots like ChatGPT, etc. It is actually an oasis to see, to hear, and just be in contact with people that do research and develop products that are not in these very, very narrow subfields. And this is how AI has been in all these almost 70 years. A very, very, very wide area with different influences, with different subfields. And we have now, unfortunately, only having attention in only one specific kind of AI. But that's not the only way to do AI. There are a lot of different techniques over the years, 70 years. And I am very, very grateful, John, that you accepted to come to Berlin in your tour, presenting the book. The latest one he has already written related to one of the theories he invented. So, meine Damen und Herren, we have today John Ball. Beth Carey is also with us, and John will tell us a little bit about the theory he invented. He was also in contact with other very famous people in AI, for example, Marvin Minsky and other colleagues too. And I think it is important also to know from the people developing those products, those theories, to have this conversation. So in the scope, for example, of a lecture, a module like the one you have, it is IT management. So thank you again to the lecturer that agreed to have this as part of the module, because when you take care of IT management, you also need to know what is about managing systems that have to do with AI. And is there any different thing happening? Are there different processes that we have to take into account? Are there different ways we should test software, for example? And yes, they are. So AI brings a lot of different elements that not normal programs, software, and other techniques have with them. So taking a look at these other areas is always a blessing, but also important if you want to manage systems that have also such kind of techniques where research is done in these other areas and so on. So maybe you can take from that some learning insights for your projects you have to present 10 days, a couple of weeks. So take it as you need, and it will follow exactly. So I am we're done with the brief introduction. John will talk more about his work and what he has done, but also about the topic he wants to present today. Then this will be about 40-45 minutes, plus minus tricks. And then we will have a short conversation in something like a panel in a fishbowl. So with some chairs here, and I hope you can see us and also understand well. And we will have always one empty chair for one people that come and ask the question here. So the questions, we hope you have a lot of questions. In the one who has a question, he or she comes sit with us for a while. We have this conversation evidently loud so that the others can also hear and understand. And when the next person has a question, they change. So the new one comes, the one that sits then could go, and that's the way we will do until we then finish time. If you let me, I will remain here 5 hours or more talking about AI, but we know that it is more or less 1 hour and a half. That's the time we agreed with the lecturer. And I hope you have fun, you learn a lot, as I hope I can learn a lot too. And please, John. So thank you again for coming. And we will be recording, John. So the camera is in this direction. And maybe at the end, if you have nothing against also recording the conversation session, then that's great. If not, just tell us so that we don't record that fun. Yeah. So thank you for coming, you too. And please.
Thank you. Thank you, Dagmar. Well, I think there were a couple of good points made. Can you guys hear me at the back? All right? Yeah. Apologize for my accent in advance. This is the Australian accent. I had an American accent earlier, and I can't do that one anymore. So this is what you get. One of the points about how my development has worked was back in the 1980s. I was really interested in cognitive science. And so I studied at the University of New South Wales, which is in Sydney. And it was the first time that they'd offered cognitive science as a degree course. So over the next couple of years, I learned a lot, and I contacted Marvin Minsky. And I thought, this AI thing can't be that hard. Cognitive science can't be that hard. I'll just ask the world expert what he thinks. And so Minsky said, give me your theory. So I explained the theory, and he goes, well, yeah, that's an interesting theory. Maybe it works. But what you have to do in life is two things. Firstly, write your theory and try and convince people. That's what I'm doing here today. And the other thing is do a simulation and prove that it works. And that's also what I'll do today to give you a bit more confidence. So going back to July of 2024, I thought, I need to get a book out there. I do hour-long presentations on the internet. You can see me just talk about what the applications are of this. And in an hour, I can sort of introduce the main concepts, but it's better to summarize what the theory is, where it comes from. And what I'm going to talk about today is AI. I'm going to talk about how brains work, and then I'm going to talk about linguistics. And you might think, why linguistics? Well, if I didn't include something practical, then you'd just think that I'm making it all up, perhaps. But I'll actually show you. And so here's the book. This is really focused on what the whole big picture story is for brains. And we've got a special on the Kindle version at the moment. If you can read things that are electronic, I find that the hard copies are easier. And I've got a few copies I'll sign after the presentation today, if you're dying to read straight after this meeting. This was our book launch in Sydney. This guy here, Michael Felcher, he's the IT AI Institute, and here's my memory checker. At the University of New South Wales, which is a big university in Sydney. He's actually from Germany. He took over the lead role of AI at the University of New South Wales, and he's talking about what they're doing, and it occurred to me that there's a really big difference between the type of AI that I do, which is I'm trying to emulate humans and speech and language, and he's doing these amazing projects like looking at the entire Australian landscape and working out where cars are positioned and what's happening and what the traffic's doing. And so I thought we need to talk about the difference between artificial intelligence and all of the varieties, because one of them can be maybe computer science and the other one can be very close to cognitive science. Oh, and that other guy sitting on the side is a world-class engineer that does work with setting up scheduling. So again, it's AI, but his sort of scheduling is if you're Coca-Cola and you've got bottles being made in one plant and being shipped somewhere and having to distribute around the world. How do you write a computer system that handles all that? So he's a simulation expert, which was quite interesting. So I'm going to start with the highest capability of human beings, which is linguistics. So this comes out of the Roland Reference Grammar book. Roland Reference Grammar is a linguistic framework. It's been developed since the 1970s. Has anybody heard of it before who hasn't read my book? Yeah. So for me, thank you, Dagmar. So for me, Roland Reference Grammar, they've spent 40 years looking at the world's diverse languages and coming out with a common approach that works for all of them. And today, people don't know about it, but Robert Van Velen, who I work with closely, we have weekly meetings and I ask all these crazy questions and he always gives me an answer and then he explains why the answer's right and he then gives me an example from some language that proves that that's how English works if I'm asking the question in English. So he has this very simple model and it's very different to today's AI model. So we start with this concept of syntax. Back in 1950, Noam Chomsky said everything's syntax. Van talks about morphosyntax. So if to build a sentence, and I'm just throwing these sentences out, I haven't prepared what I'm going to say, but as I'm saying this, I've got to make up the words, I've got to build a word form, I then got to put it into a sentence. It has to make some sense, otherwise what was the point of doing it? And then you have to be able to understand it and decompose it. So it starts with syntactic representation. I'll show you what some of the other languages in the world look like in about 30 seconds. And the words that we use then use this linking algorithm that takes 20 pages or something to explain for all of the world's languages, and that gives us a meaning representation. And meaning is independent to language. And then there's this other concept over here, which took me about 10 years to work out what he was talking about, discourse pragmatics. That's context. So when you talk to somebody and you say something after something else, the context determines what you mean. You can't just take a sentence by itself, which is what linguistics has been doing for decades, and understand that sentence without the rest. So here's some real messy stuff just to show that there's a science behind all of this. So everything I introduced today has books and books written about it. The latest RIG book's 1,000 pages. And it's written by like 20, 30 authors on very specific areas. But this example at the top here, there's an English translation. The man gave the woman the book. So probably similar to German in that we have these words, we put them in sequence, and we can then get the phrases that make sense, and then we can combine it to build a whole sentence. But in that top example, and I can dig out what language that is, there's one word here. It to her he gave, I don't know what Finn means. So that word means he gave it to her. And so you have to build that word, and then the other phrases that come before it, the man, the woman, the book, get combined with that one word, and it means the man gave the woman the book. So in a lot of these head-marked languages, it's the words that really count, and then the phrases are less important. In English, if you don't have the phrases, you can't work anything out. And then there's another language there, which you'll notice that this one word here, see, third-person object, third-person subject, that's one word as well, and the rest of the sentence goes the other way. So we've got patterns that work forward to back. We've got ones that work back to forward, and to me that's just remarkable. And plus, if we only speak a couple of languages, in my case one, it's not very well, then you'd never appreciate how the world's languages work. So that's the syntax, and we have to get to semantics. So we've got this example here. The man gave the dealer the car. This just comes out of my system. You can see that the explanation for this is language independent now because meaning isn't in the language. The man does something, there's some activity which causes the dealer to have the car. The dealer doesn't have the car, now he does. And then the man doesn't have the car. Sorry, the man has the car, but then at the end it doesn't have the car. So that's the concept of gave. And then the last bit, context. Why does context matter? So if I say, I love you, what does that mean? It's just a declarative statement, right? It's just a fact. But there's another way of interpreting it. If I were to say, if somebody were to say to me, my wife, if she were to say, do you love me? Oh, sorry, do you love her? Do you love her? So there's, some sort of problem here. And I were to say, I love you, the fact that I'm not saying I'm not answering that first question, which is, yes, I love you. If I don't answer it and I just give a contrast, it kind of means, well, yeah, I love you, but yeah, maybe that other woman I love too. So that's the type of thing that comes up in context. And here, when we're answering questions, you type into ChatGPT some statement like Taylor married Ridge. So here's if somebody said to you Taylor married Ridge, what would you say? What response would you give? Just out of the blue, right? What you would say is, who's Taylor, who's Ridge, right? You can't introduce topics in a conversation until you know what those topics are about. And we have this long-term memory. You want to bring that long-term memory into this conversation, and then you can talk about it. But if you answer this question, because it's already been discussed, this is a valid answer. Taylor married Ridge. No, it was Brooke who married Ridge. So Brooke married Ridge is what that really means. So there's this unbelievable flexibility and precision in language. And if we were to look at the world's best systems today, that these are really popular. Artificial general intelligence will be here this year, apparently. I've typed in, the Wizard of Oz is a good man. What can he do? And the answer is, the Wizard of Oz, he wasn't a real wizard. And so there's a book called The Wizard of Oz. There's a movie called The Wizard of Oz. And in those stories, there's a person called the Wizard of Oz. But I happen to have a neighbor who calls himself the Wizard, and he's from Oz. So my neighbor is the Wizard of Oz. I'm talking about my neighbor. I'm saying he's a good man. And ChatGPT misses all of that and just dives into this stuff. Great. So for ChatGPT to work correctly, this is an LLM, not ChatGPT, but if the systems are going to work, they have to know who the characters are you're talking to. They can't assume it's the most probable. So those references need to be learned on the fly, and we need this concept of immediate common ground, which is in this lecture today. The immediate common ground is the people in this room, the topics I'm talking about. I can assume if I were to meet you later, I could reference this meeting and you'd know what I'm talking about. If you weren't in this meeting and I referenced it, you go, what are you talking about? So we need to keep track of the particular context, like reading a New York Times article versus not having read that article. So there's always this background knowledge plus the immediate knowledge. So general common ground's the concept for the background knowledge. So it's not a big context window as people talk about. It's about really understanding what's going on. And context is the missing piece. On the internet at the moment, when somebody says, wow, this is great, we're going to have superhuman level intelligence tomorrow, I say, but it doesn't understand what these words mean. It doesn't have the background knowledge for those words. I want to put this up because this is science. This is linguistic science, and all of the world's languages build sentences made up of this type of structure. There's variation, but they all look like this. And if you want to take a complex sentence and bundle it into part of the sentence as a phrase, they all look like this. Maybe the orders are flipped, but the concepts are the same. So in English, the company's construction of the bridge in New York City was done a month ago. That whole sentence is bundled into part of the sentence, and then you extend it with one of those. And here, Sally's 2 red parrots is a reference phrase. So if anybody here has done a lot of linguistics work, and you've learned about the parts of speech, nouns, verbs, adjectives, adverbs, prepositions, conjunctions, the teams today that work on AI with that type of technology, they struggle with what part of speech is this thing? Even the people can't work it out. So the good news is in the semantic side, on the meaning side, there's only 2 moving parts. There's reference, which are things, and there's predicates that relate those things. So I'll just say this as a one-off in case it helps. But if you have a predicate, it always has an argument, maybe 0 to maybe 3 or something. And so a predicate as the moving parts, where it disambiguates what's being said based on the fact that it only allows certain arguments. So if I say I like you, well, like allows an animate object connected to an inanimate object, so we can resolve it. Today's LLMs have to do all of that with statistics. So go through 1 trillion documents, find out what's the probability of that word being used with this word, and then it's not generalizing until you do additional things. Okay. this is an example of how you would break down a sentence in a language, and I'll show you in a second how it works. But so we've got this very awkward sentence. The cat ate the rat continuously, slowly, on the mat today, evidently because it was hungry. And you have to work out what the syntax is. That's on this side. I call it a consolidation set. And then we map it to its meaning. And its meaning is layered. So the main concept here is the cat ate the rat, which is in the middle here. But we can extend it with because it was hungry, which sits further out. So as we're in conversation with something, we're taking the sounds that we hear, converting it to words and phrases, and then we're working out what its meaning is. And once we're at the meaning level, the great part is you can do a comparison between two meanings that have thousands of different ways of being expressed, and that meaning then is a very combinatorial reduction of complexity. So the issues back in the 1960s were, if you want to parse a sentence, you have this combinatorial explosion. You know, give me 20 words. Google talked about this in 2016. Give me 20 words and I'll give you 20,000 possible interpretations of that sentence. Now, the only way you can solve 20,000 possible interpretations is with statistics, because no human being is going to write a program that takes into account 20,000 possibilities. And that's only for one sentence. So once you get into the real world of language, you're getting into these exponentially large numbers. If you use this system with meaning, you're taking thousands of possible ways of saying a sentence and converting it to one meaning. And my argument is that that's how animals work. We have this innate meaning that we can recognize, and we can then manipulate it with language. There's some language. This is role and reference grammar again. There's some language-specific stuff. That's the other diagrams. It's the vocabulary and the phrases. And then there's this universal part, which is the meaning interpretation, and there's a bunch of standard interpretations. And next time I come here, I'll try and book an 8-hour segment, and we can run through everything. Okay, the concept of C. That's a meaningful concept, right? Now, language is very... There's a bunch, like 24 different permutations of meanings that you can put together with the word C. And I just went through and I looked at the English most popular words that use C as the basic meaning. So if something passes the window and you don't see it and suddenly you do, and then you don't see it again, there's a word for that. It's called glimpse. But it's still seeing, but you see it only for this period of time. If I want to cause somebody to see something, I use this word, show. If I want to have an activity, I can watch something. So the difference between a state and an activity, if you see something, it's just the state. You can't see something quickly. You can watch something intently, but you can't manipulate states with time because they don't change. I am quickly tall. Yeah, doesn't work, but I am walking quickly does work. Now, if you want to understand the limitations of large language models, you can either do it yourself, which is a huge task, and Dagmar is extremely good at this, or you can look at people that are experts on the internet and just steal their work. Use their work. So this guy, Tom Dietrich from Oregon, he's a professor that in the 1970s was working on machine learning. So as the whole concept of machine learning came about, Tom Dietrich was in the center of all of that, working out the best ways of exploiting it. And he's continued with expertise right through deep learning and right through to LLMs. And what he's saying is that, which is really fortunate for me, an LLM is a statistical model of a knowledge base because it takes all of those words and it works out the statistics between the words. But it's not a knowledge base. So the difference is, if I can tell you that the next word is likely this, I can string them all together and I can give you something which looks like a human-generated sentence. But it's not referencing the original, it's only referencing the statistics of it. And he then says, what should we be building? Well, we want linguistic skill from world knowledge. So the whole concept of role and reference grammar is you take the linguistics and you convert it to meaning, and you then relate the meaning, which is knowledge. So that's really good, because that's what I've been working on now for 20 years. You want this episodic memory, which is immediate common ground. It's our current discussion now. And you want to keep track of world knowledge. So his view is that if you converted large language models to something else, the something else should be this. And he finishes with, there's many details to be worked out. And today I'm offering you a book which explains the reason for how those details get worked out as part of cognitive science. When I say cognitive science, for me, it's extremely important that when you're working in a science, it all comes together. So, there's the book that I've just written, which is explaining a lot about how our brain works and how we can add language to it. But in cognitive science, you have to use everything. So this is a guy called Daniel Kahneman, Think Fast, Think Slow. And he, 800 pages or 600 pages. He's talking about why does this work for people and that not work for people, and how does this operate? So if you can't explain that in terms of your AI, then you're probably missing something. And equally, Jeff Hawkins, he's a guy that, similar time frame to me, the guy that created Palm Pilot in Silicon Valley. He's been really interested in how brains work, and in this book he explains the latest research of how you've got cortical columns and how things connect, and then he's got his theory. So if you can't explain his observations, you don't have to agree with his theory, but if you can't explain his observations, then you're missing an opportunity for your theory to be better. Okay, so for the end of my preamble, strong AI in 2025, we're talking about AGI. Are you guys hearing AGI is just about here? Yeah. So what that means is that human beings are being replicated now. This year, 2025, we've solved all the problems. So we've spent 70 years, we haven't solved the problems, and in the next couple of months, it's all being solved. Right? I don't buy it, and I'll show you what's missing. But if you think of AGI, it used to be called strong AI. So you want to have a machine that's conscious like we are. You want sensors so it can judge that the wall's 15 meters away, roughly. You want to be able to say, that's a water bottle and that's a chair. Those are chairs. You need to be able to identify all these things in real time, because if you have a driverless car that's driving down a wet road, so you can't really see the road very well because it's raining. On the left-hand side, let's just assume there's a sheer cliff, and you'll definitely die if you go off the cliff. If you go to the right, there's a truck stop there with its lights on, and if you go to the right, you're going to hit the truck and probably die. And in front of you, as you're going around the truck, you can see something in the road. Now, as a human being, in about a quarter of a second, you're going to work out what that is. And if it's a child, maybe you go off the edge of the cliff or drive into the truck because the child is so important. Maybe it's an animal and you don't care, you'll drive over it. But humans in a quarter of a second will work that out. And today's devices with the machine learning model will say, oh, we weren't trained for that particular thing, so unfortunately we had to kill the baby or something. So when they're predicting strong AI this year, that's what they're saying is going to be part of it, and it's not being worked on. So cognitive science, pattern theory, which is my brain theory, and role and reference grammar are parts of the solution. But let me do a quick demo to show you what the software looks like. Okay, so here's a sentence which is probably too small for you to see. This comes out of PubMed, so a resource for medical purposes. In PSS, interleukin 33 is released in the extracellular space from damaged salivary cells upon pro-inflammatory stimuli and/or dysfunction of epithelial barrier. So a bunch of new vocabulary. We've matched the whole thing. It's a statement. It's a positive statement, not negative. It was present tense. And what does it mean? It means that this stimuli or the barrier does something which causes the pro-inflammatory stimuli to not be in the damaged salivary cells, but interleukin 33 is in that extracellular space. So my argument of just showing you this example isn't that we could do all of this today, but it's possible with the technology to get causal relations, to understand what that sentence means. And if you then built it up, you'd have knowledge. So let me just have a look. On this page here, we've got meaning and conversation. So on the meaning side, we're just saying if I put a sentence in, Susan is tall, it just gives me it means that Susan has this property of tall. And so it's just breaking down the meaning, and this can work for any of the world's languages. If we go to conversation, and we were to put in a fact like Susan walked, and then I ask a question, who walked? What we're using is the meaning of Susan walked to then be interrogated by the question. So we can recognize what questions are, and therefore we can work out what the correct answer should be. So you're going from language to its meaning, then you ask a question, you compare it to the stored meaning, which is your context, and then you have to produce an answer, and the answer comes in whatever language you want, because the meaning is common, and it's just the language that's specific. So that's what that engine is doing. So does that make sense? I see nods. How do we put this together? So it's not being put together with statistics. So we don't need to spend $100 million or 100 million euros in order to build a training set with all of the world's knowledge together. We're simply putting in a dictionary of things like food, and these are, this is just normal programming, a normal database model. So we have a few relations here to say that what's that? Food is a type of entity, and then the forms, it's how it gets used. So a bunch of relations here. I'm trying to get to the bottom where it's got the words. So here we've got the concept of food. So in English, you don't say food and foods. The foods I ate were good. You just say the food I ate. So the plural and the singular are only in that one word. So that's the system. So let me just finish with this is my introduction. How are we going for time, Bess?
At the nearly 35-minute mark.
Okay, good. So I'm going to just give you the science behind how these two things work in a moment. So again, why should you listen to me? I know it's a bit late for that, but I've been doing this for a long time. So when I was 9 years old, I was working on a mainframe computer at my father's office. It was the thing that then became the internet decades later. So I've always wanted to be like Scotty from Star Trek. I wanted to be the one that, the Enterprise was about to blow up. I wanted to crawl down that tube, tighten the screw, and save everybody. So that's since 1972. But in 1983, my professor said to me, we're never going to understand how language works. It's too complicated. The brain's too complicated. So that set me on a mission for 20 years where I just worked out, I cared about how can a slow brain do what supercomputers can't do. And the end result was pattern theory. And it went through a bunch of steps, like in order to do something as quickly as the brain does, it couldn't be following the type of process that a computer would use. So in a computer, you just do a loop, and you loop over 1 million items, and in a millisecond, it works out the answer. But the neurons in our head work at about 2 milliseconds, and when we come around that corner and we see a baby in the street, we recognize that in at most 100 neuron activations in sequence. So there's this big parallel thing happening. But then the question is, well, is our brain just a whole bunch of these people sitting in each neuron working out, I see this stuff coming in, what do I do with it? I couldn't imagine how that would work. That would be impossible as well. And then I realized, well, you need to improve the way search operates. If you fill a stadium with people and you're a computer and you want to work out where a particular person is, you can sort them by name. And so 80,000 people in the stadium, you go and ask 80,000 people, what's your name? You sort them, and then with the search, in a few steps, you can go and find the right person. But the thing that you couldn't do is you couldn't ask a question like, who in this stadium has red shoes, a hat on, and something else? It's not possible. So the solution to that was changing the way we actually store the information, and it becomes no longer like a computer. It's like a brain. There was something coming up. Yes. Okay, so this is from Oliver Selfridge. This is the 1950s. Can anybody see any words there? So the argument is that even though the H and the A are exactly drawn the same way, we recognize it as the cat. So it can't be the symbol recognition. It's got to be something bigger than that. And it's possible that that means the cat, but it's also possible that it means some company name, a company acronym. And the only way you can tell is by interrogating that in a sentence and working on it. And here's the challenge for, I'm just putting up a common expression there. It looks like northeast and 14 and 10 and a south maybe. So maybe that's coordinates. But we can work out what that is with a little bit of thought. So we've got, let's see, there's an E, so I can make the sound E, there's an N, maybe there's a pattern that's coming out of all of this. There's south for S, 1410. And if you keep working through it, this is an example where if you haven't seen it before, your brain's able to work it out by going through all of these permutations, thinking about it and seeing what makes sense. And then finally, at the end, you can go, oh, look, NE1 for tennis. And there you go, you've got an answer. And next time you see it, you might just jump straight to this because you've learned it. And so for us to speak language at the rate we do, we want to be able to go from one thing to an association to another association to maybe some more and get the answer really quick. Otherwise, you'd have no chance of recognizing what I'm talking about today. And the goal of any computer system or any AI system is to basically follow this rule. Don't search unless you know there's a reason to search. So for example, in today's large language models, you go from one word to the next word, and you might have 10 million possible next words, and so you've got to keep track of all of those. But unless you've actually experienced that combination in sequence, then you don't want to look for all of these words that aren't the next word. And so by getting away from the statistical model and just looking at what is really a possible link, that's the way I can get the performance out of a laptop to do what we're seeing here. Okay, I've got a good joke here. When we were in San Francisco, it was a big bar, bigger than this room, and I could see free beer in the back corner. And so I walked over there. I'm trying to get through all of the people, and as I got closer and closer, underneath the free beer was a label that said tomorrow. And so it was very disappointing. The free beer was tomorrow. And where we are in AI is everything's about 10 years away up until now. So this is the history of AI. Cybernetics came out in the 40s, and then cognitive science and AI was announced in 1956 at virtually the same time. And at that point, if you were to ask somebody, they would say that within 10 years we'll have a solution. And it's always been about 10 years, up until nearly the present. And now in the present, people are saying it's coming out this year. But the same problems are existing today that were existing back then. So here, Goldman Sachs, 300 million jobs could be lost due to automation of AI, so very scary. And Sam Altman is predicting that they now know how to do AGI as we've traditionally understood it. So that's the automobile example. And it's happening, we believe, 2025. So we'll see 2026 later this year, and we'll see in a decade, maybe next year. So we haven't succeeded. I'm just going to finish with this example from a large language model. So this is using Leo, the Brave browser. And what it's showing here, I've looked for the AI Dartmouth conference. So this is the 1956 creation of AI. And the participants there, we've got John McCarthy, Marvin Minsky, a guy from IBM, and a guy from Bell Labs, the guy behind information theory, Claude Shannon. And interestingly, other notable attendees included Alan Turing. Now, he's my hero. And this is written by machine, and they were interested in machine learning. They're going to be using machine learning. This is, 1956. And then here we've got some Wikipedia content. So the difference is Wikipedia is written by people, LLMs is written by machine. So when you search on Wikipedia, you see that Turing died in 1954, so he definitely wasn't at the 1956 conference. Machine learning was named 1959. What they talked about at that conference was machines that learn. So they wanted to build a machine that would, like a child, it would sit there and as it experienced the world, it would learn. That it was learning by machine, not machine learning as in the current concept of it. But the machine itself can't cope with that, and so that's a limitation. And what do we want to do? In the book I talk about 7 killer apps, because people are saying AI is just so fantastic, we're making such amazing progress. And one of the reasons they say that is when there's a new field of AI that comes out, they'll build a benchmark for it. Usually the people that are working on it build the benchmark. They then pass their own benchmark and they say, look at how good we are, we're doing better and better. And then they extend it by adding more tests that they can also pass. And then they go, look at this incredible progress. We're going from not having any tests to now passing all of the tests, and it's just all accelerating because we've got 1,000 people working on this. But when you compare it to the actual goal of AI, there's no movement. Where automatic speech to text, if you use the dictation function, it gets the words that you say, but not accurately. If it makes a mistake, you can't say, oh, no, that's the wrong word. I use the example in Australia of, I'm on Wallamata Road, and Wallamata is an Aboriginal name, so it's not really English, but it translates that into Water or something. And the only way you can correct that is, I don't know, going into text, reversing all the way over back to the beginning, and you could try saying it again, it never works, or you type it in. So the whole speech recognition is broken. It's not interactive like a person would be. So that's automatic speech to text, translation between languages. I keep getting told that it works, it's done, nothing more to be done here, but would you take a document produced in one language, convert it to your language, and then say, this is perfect, I know everything that the original document said? The Speech Genie project is something that we're doing with language learning. We're taking a guy that's a world expert in teaching Mandarin Chinese people to speak English. They do these crazy concepts like they get people to put headphones on and listen to the sound of English for 20 minutes. And as a result of that, their brain starts to pick up the patterns. So when they then move to the next stage, which is introducing words, their brain is already primed to recognize the language. So there's a whole bunch of tricks that you can use using cognitive science to improve language learning. And then I've got driverless cars. We were promised driverless cars in 2016 by Elon Musk, and it's a couple of years away still. Although I think he said this year it'll be working. Internet search. So internet search is a solved problem, but not to my way of thinking. Because if I want to get something on the internet, like I want to buy a car, and I say, I want a car, it should be these colors, I want it in this price range, you know you're not going to get what you want. And what it should be is interactive conversation. But that's what the Google guys were originally looking to do with search. Just say what you want and have the system come back with what you need. So we've got things that are killer apps. This will revolutionize how we work with machines once all of this happens. And we've been 10 years away from all of them for the last 70 years. Which brings me to this. I've got one video, and then I think we'll move into the question section. There's this guy, Moravec, who with Marvin Minsky and Rodney Brooks, who's an Australian from Adelaide, who was the AI lab leader at MIT. The hard things are easy and the easy things are hard. So things that machines do really well, things that are easy for machines, like memorizing the entire phone book or the names of everybody in a country. Machines do that really well. People can't do it. The other thing is for a machine to walk across the room and get to the second page here, that's easy for people and it's impossible for machines. And if you could do that, there's just lots and lots of applications that are possible. And my point is that the things that are hard for machines are these paradox things. It's the animal type skills. And I just want to show you a video that talks about the difference between...
Time for the Michael Jordan, if you want.
Yeah? Okay, this is classification of AI. And this is a really good way to remember it. So do you guys, have you heard of Michael Jordan? You know, this guy who's looks like he's about 6 foot off the ground. So a really good basketball player. And Michael Jordan from UC Berkeley came out with this amazing idea. Not that Michael Jordan, who was born on my birthday, but this guy. And he said in 2018, the revolution hasn't started yet for AI. And he was saying that the problem with AI is that it means whatever you want it to mean. At the Super Bowl this year, the American Super Bowl, you might have noticed that Coca-Cola had an ad. Coca-Cola is saying that we're an AI company. I find it hard to see how Coke is a really big AI company, but they are. So he broke it down into human emulation, things like search engines, things like infrastructure, which is Google Maps. So a system that keeps track of all of the cars in Germany, all of the roads, where the busy places are. That's infrastructure type projects. But I think there's a better way of mapping this, where all of these things that a computer scientist can do, like search engines and Google Maps, complex interactions, it's computer science, because it's not something that a person can do. Animal emulation, animals can track context. If you throw a ball or something, the animal knows that it's a ball, even though it's moving through shadows and changing shape and color. And then human emulation, language and speech, gymnastics, things that we've never seen any other animals able to do. So the cybernetics bit is the missing part from everything, which is the hard part of AI. My book subtitle, just The Final Frontier in Science. If you ask a world expert in neuroscience how the brain works, they're going to tell you that the brain works like a computer. And it's sort of a nice analogy, but it doesn't work, because it doesn't tell you anything, and it's wrong, because the way memory works in a brain is radically different. So here, that's the human vision system, a simplified form of it. And so vision goes from the eye through some old brain regions. One area comes to your temporal lobe, which identifies things like human faces. How would a computer put in one particular area the recognition of human faces? So, you know, if you lose that region on both sides of your brain and you see somebody that you used to know well, you can't recognize their face. But if they speak, you recognize who they are, because you can recognize their voice. And that's in a particular location in our brain. And going down around the back of the head towards the top, there's this location of where things are moving to. If you damage that part of your brain, and I can see this book, when you go to pick it up, you can't pick it up because your arm doesn't do what you think it should be doing, because that part of your brain controls the motion. So my question to you would be, how can a computer system do that? And the answer is, it's not a computational system, it's a pattern matching system. And as we match patterns bidirectionally from the eye right through the system, we're able to find what we recognize, like in the cat example. Once you recognize the cat, when you go back and check the words, you go, yeah, those words make sense. So the final frontier in science. Okay, and here's a dog chasing a ball. And what I'm showing you is that, firstly, animals are really good at motion. The ground's not level. The vision system, it's trying to work through grass and boats and all sorts of distractions. It's about to do a victory lap. It can run with a jacket on. That's pretty impressive. And then this is going to turn 180 degrees around. You can see its eyes locking onto the ball. It's just done a 180-degree turn, and it's jumped up, caught the ball, all legs off the ground, and the victory lap begins. So this is what animals do. There's never any chance of this dog falling over. Like, the ground's not even. It doesn't look vaguely like it's going to fall over. But here's robotic skills. So this is a group in Portland. This is a $190 million investment in bipedal robots. And that screen there, just stopping it. So this is the vision system of the great AI we have today. There's a blob here. There's a blob here, which is probably one of those baskets that it's going to move. When I'm looking at you guys in the audience, I recognize the people, the chairs, the tables, the ceiling. That's the type of skills that animals need in order to navigate in the real world. Tesla's very popular at the moment, but you'll notice that it's got touch sensors in its fingers, but as it puts this egg into the egg cup, it drops it. Right? People don't do that. We would place it in the egg cup, feel that it was in correctly, and then we'd move our hand away. And so even though, I wouldn't recommend you do this at home, this is how robots can stand up. It's bad for your back if you do that one. So the point is that the robots aren't yet at animal level. If we can get animal level to work, that would be great. And here's my analogy for our brain. So if you're a fish or an amphibian or any mammal, brains evolved to take sensory information, the brain somehow controls it and then moves muscles. So the arms race for the last, well, certainly hundreds of millions of years, 500 million years, has been around just getting better senses and motion for survival. But you can see in the dog case, context is there. So when you bounce a ball, it knows that ball is a thing, it's an object, and it's able to chase it and catch it. And I put consciousness in this space for animals as well, because if you're an animal and something starts eating your arm, you want to pull away and treat all of your cells equally. And then the human extensions are things like language and gymnastics and the like. But here's what I was taught AI needs to do. You take this model, 8 points to create a cube, and you give me the coordinates, and then I can put it through a processing system and I can work out where the lines should be in three-dimensional space, which is a nice concept, but the trouble is, how would a brain do that? How would a brain get equations? And you can say, well, evolution's amazing. Well, you can, but how would it do it? Because you want some animal to also be able to do that. Versus, I see these boxes, and if I can keep track of the fact that it's the same box and somehow link it in this bidirectional model, I could match that much more easily than I could generate the coordinates and the lines that you'd see for this, and then take into account shadows and colors and so forth, reflections. So that's my distinction between the computational model at the bottom and the pattern-based model, the pattern theory model at the top. And interestingly, machine learning works more like the top model, but again, if I've got a book and I'm moving it and it's changing image, you still recognize it as a book because your brain has this a brain region that's focused on motion. In fact, I'll just finish with that concept. So, if you lose your visual motion areas of your brain, and you're watching a car come towards you, as a normal person, you see the car coming towards you, and it's smoothly getting bigger and bigger and bigger as it gets towards you. But if you lose those brain regions, what you see is in the road there's a car there, and suddenly it's vanished. And then it reappears closer, and then it vanishes, and then it reappears closer. So without a specific brain region, which looks like all the other brain regions, it's able to give you this sense of awareness of motion, of visual motion. And again, you have to work out as a cognitive scientist how that can work. Might leave with this one last thing, because I like this one. So when you look at a brain and you put in cat, what we see is that brain regions get activated and they then project to other brain regions, and those regions are active, and then some of them die off and something's happening, but you can't quite tell what's happening. But if you label them like I'm doing here, if we were going from vision to something that's recognizing letters, and then those letters come forward to sequences, the CAT sequence is been matched by the CAT in the right order. And so we're able to say, well, that recognizes cat, and we can keep all of the recognition of the actual letters for cat in a separate part of the brain. So it's just a hierarchical approach. But when we look at a brain, there's no labels. All you're seeing is neurons activating and in very complex structures in these cortical columns and so forth. So it's a better analogy once you actually see the labels being used. But the rest are more simulations, and I think that's the key point I wanted to make. So maybe we'll move on to the next segment of questions.
Thank you so much, John. So we will change a little bit here. Something.
Thanks.
The
interrogation chair?
interrogation. This is the weird. Well, like this, the thing. I will sit here and then we have the guest coming to us. I will start. So I bought your book some time ago, and I am 2/3 into the book. I have skimmed the last third, so I know what it's talking about and what you wrote. But I like to communicate with the book, also making notes and arguments and going back, something I cannot do with the digital underparts. I like to handwrite things and sometimes erase and then put something else. And I noticed that it is better for my brain and then I retain information a different way compared to doing that in a reader, digital reader, etc. So I have handwritten some pages of the book, and I have a lot of questions, but I will only pose 3 of them, which I marked here. And they are almost all related to the very old topic of AI, and I need my other classes. And one of them is the following. Maybe I go to the last one because this has to do with what I hope also for students and in case we have now with AI. And I read this is page 80. So brains work with the full context, as you already also have explained in your talk. So the big problem, however, today with generative AI is that the output cannot be trusted. So with the chatbots, with the large language models, you cannot trust the information that comes out. You have always to verify. Sometimes it's correct, and other times it's not because of the statistical way of coming to the next words, etc., like the chatbots we have today. So it cannot even be relied upon to generate the same answer the next time, a weakness of a stochastic system. And what I wrote on the module was exactly, so that is what is happening. And this has implications for students, because students still are not the experts in a domain, and maybe are not able still to discern what is true, what is not the truth, until they know what is valid. Yeah. Something we already know, we can say, well, that's not right, but something we still don't know, it is very difficult to not know or to know whether it is wrong or it is true. What is your suggestion? Because now it is very, very difficult to convince not only students, but worldwide, the people, to shift from what we have now, which is this amazing momentum in the media about what AI is, which is very different to the reality of AI. what is your suggestion? You told us a couple of times here to do what is in the book, what I am telling, what people are telling, but we still cannot convince sometimes ourselves to move. In your experience, what is needed to change that?
Well, I think one of the key points is that universities need to be using the expertise that's here to make decisions. We don't want, I don't think you want industry telling you what the answers should be based on what they have commercial benefit from. For example, I keep hearing that programming is going to be revolutionized in a couple of years because you don't need to write your own programs. So my experience with the generative AI for programs, which is this amazing area that should be perfect, was my code base is like 80,000 lines of code. So there's a lot. I've got a good picture of where everything fits, and I can go and change things quite rapidly. But I was developing something new, and I needed to create this header for a class. So in the class, you put the name, you put its arguments, and then you write the code after it. And the mechanical typing out of that is a bit annoying because it's like 50 letters or something. And so it prompted me and it said, do you want this? And I go, yes, boom. And so then I do my regular tests, and we've got, 10,000 tests or something, which all pass. And suddenly I was getting every other test failing. Like, it's about 50%, maybe a bit less. And so I looked at the changes I'd made since my last test, and there were maybe 50 files, 100 files that had been changed. And so you look at them all, they all look good, everything looks great. The thing that's not working is still one of those things. I don't want to back out, of all of the work that I'd done. So I start tracing, and after about 6 hours, I find out that this thing that had automatically typed in for me that saved me about 30 seconds, they'd swapped the parameters because the parameters look better if you swap them, but they're wrong if you swap them. And so the names were wrong, then the code was wrong, and it was swapping something not really directly involved in my process, but it's certainly broken. So after those 6 hours, I swapped them. So I'd saved my 30 seconds, but cost 6 hours. And I think that's the challenge with generative AI, that if it did what was being proposed, if it just wrote my code for me, great, go and do it. I don't have to program anymore. But until it does, and it could be decades before it really does it properly, then you've just got to be super careful. And I'm pretty much following the right standards for coding. We've got tests, I don't use unit tests, but that's another problem. In fact, if you're a computer science people, one of the issues with machine learning is that you bring in this data, you create your training set, and depending on what the data is, it's going to produce different answers. When you write a normal program, you write a piece of code, you know what you're putting in, and it has to do particular functions to get out the end. And so the unit test is just testing this piece of code where you know what's going in and it produces the right answer. But once you get into a machine learning environment, it's the data that produces the answers. And so you can't write a unit test against it. You can only write an integration test. So you can test end to end, does this thing work? But you can't test, does this particular unit work in all cases. So for me, one of the things that we focused on was, by not having a machine learning engine driving this, we're able to test every single thing. So when I use the term predicate, some predicates have like 1,200 variations that are possible to correctly resolve that. We can test all 1,200 of them, and if there's like 250 classes in a language, it's not that big a job. It's not one person job, but it's not a very big job to make the whole thing testable. So the next step from generative AI is to have a fully tested code base that aligns exactly with your dictionary or your meaning representations, that's therefore able to be trusted. On the more general side, So that's the experience with coding. On the more general side, I showed you the example of the Alan Turing, being at an event 2 years after he died. I think it's going to be very difficult to rely on these systems until there's a knowledge base that is driving the answers. It's going to be very hard to rely on it. So I'm not sure what the answer is, other than the universities taking a lead and simply pushing back and saying, with skepticism, okay, well you can try this, but now how do you fix it if it's not working correctly?
Comforting that there are other cognitive AI approaches and other brains applying themselves to this problem, that what we're seeing from exposed with the problems with the large language models is not the only approach. But it does take a group such as us and others that we've come across in Austin, Texas, looking at what is a brain emulation approach that isn't the statistical one that's dominating at the moment. So even though it dominates, it's not the only approach that's out there. Things of original research, it's validated, and John has shown before in reference grammar and his brain science. It does take funding and effort to get these things off the ground, but they're happening around the world.
Yes.
So maybe related to that too, the cybernetics. So we know that John McCarthy, one of the things he wanted was not to use or to mix cybernetics with his proposal at that time for the Dagmar conference.
Yes.
He wanted explicitly to leave out cybernetics. We see from your talk, from your book, and also from other research projects, that cybernetics is important. So it's having these feedback loops, for example, back into the system to get information and to simulate also how animals work or solve a task or do something. And this is coming back too. And what do you think it is? Maybe there is not only one solution, one way, one model, one theory, but unifying theories is very difficult. So what do you think it should maybe be the path? A hybrid that takes the best from some approaches, or putting away the approaches that make no sense and then look into a different direction?
I think diversity is the right solution up front. I'm as contrarian as they come. So if I couldn't do it and imagine that the brain is also doing it, I wouldn't use it. So I've got no statistics in the code base. People ask me, do you want to use neurosymbolic architectures, which is argued to be the next generation? We met with this guy in Austin, Texas, a couple of weeks ago, Peter Voss, and he's one of the authors for the AGI book, Artificial General Intelligence book, and he's one of the guys that named it in 2002 or something. So his goal is to create a machine that's intelligent with human-like intelligence built into it. And in our discussion, my challenge for him is, what's intelligence? Because if you're building vision, is vision intelligence? Because then you've got to say, well, that's an intelligent fish vision, and that's an intelligent human vision. I couldn't see how you would do it, and we only had an hour to talk in Austin. But he's got a plan of how he can produce AGI, so general modules that drive a system. I've got a different approach, and I think I'm tying mine more closely into what I see brains do. But at this stage, until we've got something that works better, you might as well just be an engineer and mix and match whatever produces something that works. When we look at the technologies today, if you want to go to Mars, you probably have a pretty good start of how to build the rockets and the fuel and so forth. At some point, somebody might iterate and work out a better gravitational field that will move the rocket better, and everybody will move from fuels to gravitational techniques. But for now, I just keep things very fluid, and certainly not do the model that we're seeing out of Silicon Valley, which is it has to be machine learning, it has to be large language models, and we'll apply that to cybernetics, because I just can't see that that's the right approach until it starts to work properly.
My last question before we invite the others. You in your book differentiate between engineering and science. I think this is important also for the students, because some of the time it is only engineering programs, but not doing the science behind that. So they are modules which are, separated, and they don't mix normally the case. If you maybe could briefly tell them this difference, so why it is important in order to create such systems to put more focus in the science part, for example, how the brain works, etc., and not actually always or only in the on the engineering part.
Right. Yeah. So I've had the terrible experience of being trained as a scientist. So I've done cognitive science, and I was taught how things should work. And then I sat at a desk for 6 years and kept finding things that I couldn't make work. So parts of speech, the example of 20 words gives you 20,000 possible combinations. It seems to me there's something not right there. And I then challenged the fact that the parts of speech wasn't the right solution, and got some help. We reworked it, and suddenly we went from having lots and lots of ambiguity to a couple of possible answers that we could pick from. So what's going on here is, if you look up the Wikipedia page for natural science, or the types of sciences, natural science, formal science, Silicon Valley in particular is fanatical about formal science. So if you can build me a bunch of rules and apply those rules for every scenario, you've got a formal model. And the types of formal sciences are things like mathematics, computer science, statistics. They work because the end results work, and you can't trace it back to an experiment. Empirical science, like Galileo's work with looking through his telescope at the planets and making observations of seeing moons, that allowed him to have a theory, to then look through his telescope and see what was happening, and then keep refining his theory based on observation. So my argument is cognitive science, by definition, is empirical. We've got people, if I say, what do you think of Fred and Helga? And somebody says, who are they? Well, that's a key point. Until you know who Fred and Helga are, you can't talk about them. So our machines should be doing the same thing. That should be part of the science, the empirical science. If you just take a large language model, you put in Fred and Helga, it dives into its knowledge base, does all of its statistical work, finds that Fred and Helga were in some cartoon, and then it assumes that you're talking about that cartoon because you've just skewed, or you biased the whole system towards those words, and you might not even have ever heard of them in that scenario. So my point is that empirical science should be for something new at the very front and center of what we do, so that our models keep reflecting what the literature in that area does. And then later on, we can start refining and improving the models once they work.
Thank you. So the questions. Who has the question? One is the problem.
There's.
Yes, please.